Jai Hind everyone. I am Krishna Gupta. I am assistant professor in Electronics and Communication Engineering Department in Ajay Kumar Garg Engineering College. This is lecture 2 of the subject integrated circuits. In this lecture, I am going to discuss about active wideband pass filters. So contents are active and passive filters. We'll start with the introduction of active and passive filters. What are the differences, what are the advantages of active filters, and after that we'll discuss about active band pass filter, then we'll come to the wide band pass filter. So starting with the filters. So filters are the circuits which are used to pass a particular range of frequency that is desirable, and it attenuates, it blocks the other frequencies, that is filter, to filter out the desired frequencies, to separate the desired and undesired frequencies, right? So filters can be classified into various parts. The first classification is based on the techniques, that is analog and digital filters. Analog filters are those filters which are used to process analog signals. Digital filters also process analog signals, but it processes analog signals using digital techniques. So here we are talking about analog filters, right? Further, filters can be classified on the basis of the component used. On that basis, the filters can be classified into two parts. One is active filter and another one is passive filter. So as the name suggests, passive filters are those filters which utilizes only passive elements, which uses only passive elements. For example, passive elements are resistor, capacitor and inductor. If any filter is made up of only these passive elements R, L, C, then these filters are called passive filters. Active filters, it uses active elements. For example, one of the active element is op-amp. So along with op-amp in active filter, along with op-amp, we also use resistor and capacitor. But op-amp is there. That is most important part of active filter. So we can differentiate between active and passive filter, and we can understand that what are the main advantages of active and passive filters and what are the limitations of active and passive filters, right? So we can see that in passive filters, since there is no active element involved, so we don't get any gain in case of passive filter. So one of the key point for passive filter is it does not provide gain. It does not provide gain, because if any circuit is made up of only passive element, then it cannot amplify the signal, it cannot provide the gain. While in active filters, since it is using op-amp, so active filters, it provide gain. So that is the difference between active and passive filter. That is the first difference. Like active filter, it provides gain, and passive filters, it does not provide gain. So that is the advantage of active filter over passive filter. Another advantage of active filter is there is no loading effect in active filter. There is no loading effect in active filters. So we can understand that why there is no loading effect, there is no loading problem in active filter, because here we are using operational amplifier in active filters, and for op-amp we know that the input impedance is very high and output impedance is very low, and in active filters we prefer non-inverting configuration because of its high input impedance, So that is the second advantage of active filter. There is no loading problem, but there is a loading problem in passive filters. But there is one limitation of active filter. That limitation is, since we are using operational amplifier here, so the gain bandwidth product of the filter, it is limited by op-amp, because for example if we are using 741 IC, 741 op-amp IC, so for 741 op-amp IC the gain bandwidth product is 1 megahertz. It means that if we require a filter of 100 megahertz or in gigahertz range, so we cannot use 741 IC. Similarly, the another limitation of 741 IC is speed, about speed. The slew rate is not good for 741 IC. So for high speed applications, we require other op-amp IC like LM318. So the point is that the gain bandwidth product and the slew rate of the op-amp, if there are issues with gain bandwidth product and slew rate of op-amp, then obviously that will be the issues with the filters also. That is one of the limitation of active filter. And as far as frequency range is concerned, so there are two types of filters mainly classified. The one is audio filters, audio frequency filters, that is low frequency filters, and another one is high frequency filter, that is also referred as radio frequency filters. So RC filters means if we are using resistor and capacitors, these RC filters are low frequency filters, or we can say that audio frequency filter in audio frequency range we can use. And for high frequency applications we use LC filters. LC filter is used for high frequency or radio frequency. So you can understand that that can be the advantage of passive filters, because in passive filters we are utilizing inductors, so we can use inductors at high frequency, because at high frequency the size of the inductor will be less, and there will be issues at low frequency while when we use inductors at low frequency, because at low frequency the size of the inductor it becomes very large. Fine. So these are the few differences between active and passive filters, and in this class I am just going to discuss the active band pass filter. Now next one is types of active filters. Band pass filter is one of the type of active filters. There are mainly 5 types of filters, and these 5 types of filters are, the first one is low pass filter, active low pass filter. The second one is active high pass filter. The third one is active band pass filter. The fourth one is active band reject filter, that is also called band elimination filter or band stop filter, and the fifth one is all pass filter. So these are the few filters in the types of active filter, and we are focusing on band pass filter in this particular class. So band pass filter, as the name suggests, it passes a particular band of frequencies and it blocks the other frequencies, right? So as far as wide band pass filter is concerned, so when we draw the frequency response of wide band pass filter, frequency response means on x axis there is a term frequency, and at y axis we take voltage gain in dB. That voltage gain in dB, it will be 20 log mod V naught upon V, right? So gain in dB versus frequency. So the graph for wide band pass filter is this one, right? You can see that a particular band of frequency is passed, and there are two cutoff frequencies involved. One is FL and another one is FH. FL and FH. These are the cutoff frequencies for wide band pass filter. FL is referred as lower cutoff frequency and FH is called upper cutoff frequency. This cutoff frequency, it is also called minus 3 dB frequency, and the maximum pass band gain is this one. Let's say this is AFT. AFT is the total pass band gain, right? And here we can mark the pass band and stop band also. So from this graph we can see that this one is pass band, because in pass band we get the maximum gain, and these two are the stop band, because in stop band you can see that the gain is reduced. If gain is reducing, it means that the signal is getting attenuated, right? And as far as roll off rate is concerned, when we use first order high pass and first order low pass filter to design wide band pass filter, then the roll off rate, we can see that the roll off rate will be, this one is plus 20 dB per decade, and this one is minus 20 dB per decade. Fine, this is the roll off rate. So here we can see that this wide band pass filter, it is the combination of first order high pass filter and first order low pass filter. If we connect first order high pass filter and first order low pass filter in cascade, then it becomes wide band pass filter. You can see that if I just draw this vertical line, then you can see that the left side, it is the frequency response of the high pass filter, and this one is the frequency response of the low pass filter. So here we can easily understand that if we combine, just if we cascade the first order high pass and first order low pass, then it will become band pass filter. It will become band pass filter, and the minimum order required for band pass filter is 2. Fine. Now if we classify band pass filter, then this band pass filter can be classified into two parts. One is wide band pass filter that I am discussing here, and the another one is narrow band pass filter. So there is one division line for wide and narrow band pass filter. As far as wide band pass filter is concerned, for wide band pass filter we say that the quality factor Q is less than 10. Quality factor Q is less than 10. And as far as narrow band pass filter is concerned, the quality factor Q is greater than 10. And this quality factor Q is defined as center frequency Fc upon bandwidth. Center frequency Fc upon bandwidth. So this center frequency Fc is under root Fh into Fl, and this bandwidth is Fh minus Fl. So if the bandwidth is more, then quality factor will be less. So you can see that for wide band pass filter the bandwidth is more, that's why quality factor is less, and for narrow band pass filter, since the bandwidth is very narrow, that's why quality factor is more. So this is about a wide band pass filter. Now coming to the circuit of wide band pass filter. So we can imagine that how we can draw the circuit of a wide band pass filter. So for that, firstly we will have to draw the first order high pass filter, then first order low pass filter. So obviously it is an active filter, so we are taking this op-amp here, and to draw the first order high pass filter, the input signal, that input signal is Vin, that is given to this capacitor C, and there is a resistor R connected between non-inverting terminal and ground. This is a capacitor C. Since this is one RC section, so it's a first order high pass. Now to provide the gain, to control the gain, what we do? We connect a resistor at the inverting terminal. Let's say this resistance is R1 and another terminal is connected to ground, and there is a feedback resistance that is connected in the negative feedback path. Let's say this is RF. So here this is the circuit of first order high pass filter. It is first order high pass filter because there is only one RC section, and the filter function is performed with the help of this RC section, and the gain is provided by these two resistors R1 and RF. Now you can see that this is the non-inverting configuration of op-amp because the input signal is applied at the non-inverting terminal, and the advantage of non-inverting terminal is its input impedance is high, that is desirable in order to avoid the signal loss. So the output of this first order high pass filter, let's say it is VO1, and this is op-amp A1. Now we need to draw the first order low pass filter also. So to draw the low pass filter first order, what we do, we just interchange R and C. So the circuit is this one, just we have interchange R and C, and again to provide the gain we are required to connect two resistors, one is R1 and another one is RF, and the output of the first op-amp A1, it is given to the input of the second op-amp A2, and the output of the second op-amp A2 is, let's say it is VO2. Now in order to just differentiate the component values, just to differentiate, we can take R dash, C dash, R1 dash, R1 dash, RF dash for first order, for first order low pass filter. Now from this circuit you can see that these two first order high pass and first order low pass filter are connected in cascade, and it provides the wide band pass filter function. It provides the wide band pass filter function. Again for second op-amp A2, the filter function is provided by R dash C dash and the gain is provided by R1 dash RF dash. And if we calculate the pass band gain of individual filter, let's say the pass band gain of first order high pass filter is AF1, let's say it is AF1, then the AF1 will be 1 plus RF upon R1. This 1 plus RF upon R1 formula is here. So you people had derived it in last semester also. So this is for non-inverting amplifier. Similarly for first order high pass filter, the pass band gain is AF2. This AF2 will be 1 plus RF dash upon R1 dash, right? So AF1 and AF2 are the pass band gain of individual first order high pass and first order low pass. So what will be overall pass band gain? Overall pass band gain, that is AFT, that is AFT, total pass band. It will be multiplication of AF1 into AF2, because both the circuits, both the filters, first order high pass and low pass are connected in cascade. So in that case the gain is multiplied. This is AFT. So this is the circuit of wide band pass filter, active wide band pass filter, because we are using this op-amp as an active element. Along with op-amp we are using few resistors and capacitors. Now coming to the design of wide band pass filter. As far as design is concerned for particular filter, so we design a filter for a particular cutoff frequency, and in wide band pass filter there are two cutoff frequencies. One is FL, that is lower cutoff frequency, and another one is FS, that is upper cutoff frequency, or we can say FL is lower minus 3 dB frequency and FH is upper minus 3 dB frequency. And it is mandatory for wide band pass filter that FH should be greater than FL. It is very much clear from the graph. You can see this frequency response. For wide band pass filter, FH will always be greater than FL. Fine. Now as far as design of wide band pass filter is concerned, so it's in fact very easy, because if you have studied first order low pass and first order high pass, then the design steps are same. So to design wide band pass filter, firstly we will have to design first order high pass filter, and then we will have to design first order low pass filter. And for first order high pass filter, the cutoff frequency we are taking is FL, and for first order low pass filter the cutoff frequency is FH. So we need to design a low pass and high pass filter for this FH and FL. Of course FH will be greater than FL, and the formula for FL and FH you had derived in first order low pass and high pass filter. So this FH is 1 upon 2 pi, since we are using r dash c dash, so 1 upon 2 pi r dash c dash, and FL is equal to 1 upon 2 pi RC. Fine. And as far as first order high pass filter is concerned, the transfer function for first order high pass filter is AF1 upon under root 1 plus FL upon F square. Similarly, for first order low pass filter, the transfer function is since the passband gain for low pass filter we have taken AF2, so AF2 upon under root 1 plus F by FH square. See, these few equations we require. We should be aware with these equations, only then we can do the numerical problems. Fine. So the cutoff frequency equations I have mentioned, and the transfer function you can derive. If you have not derived, then you can easily derive for first order high pass and first order low pass filter. You will get these equations. This V naught upon V, it is for first order high pass filter, and this is for first order low pass filter. Then of course overall gain of the wideband pass filter, it will be the multiplication of these two equations, AF1 upon under root 1 plus FL by F square into AF2 upon under root 1 plus F by FH square, because both the circuits are connected in cascade. Fine. So we will understand it with the help of a question. The question is design a wideband pass filter with FL equal to 200 Hz, FH is equal to 1 kilohertz, and passband gain is equal to 4, and further we will have to draw the frequency response and calculate the value of Q, that is the quality factor. Fine. So in the question FL is given, this FL is equal to 200 Hz. So firstly we will have to design a first order high pass filter for cutoff frequency of 200 Hz, because FL is the cutoff frequency for first order high pass filter. So for that we need to calculate the value of R and C, and we know the equation for FL, that is FL is equal to 1 upon 2 pi RC. Now FL is given 200 Hz. Fine. So one equation, two unknown. Again we will take some value of capacitor C. Let's take capacitor C 0.01 microfarad. Normally we take C less than 1 microfarad, and let's take C is equal to 0.01 microfarad. You can take any other value also, but of fixed value it will be better, like 0.1 microfarad you can take, 0.0047 microfarad you can take. So the numerical answers will be different for filters, but the design steps should be clear, right? So from this equation we can calculate the value of R. Now we need to calculate the value of R1 and RF. For that we know that passband gain AF1 is equal to 1 plus RF upon R1. Now see, the passband gain is equal to 4. If the passband gain is equal to 4, what is this 4? 4 is total passband gain, that is given. And what is AFT? AFT is the total passband gain, that is the passband gain of first order high pass filter into passband gain of the first order low pass filter, that is 4. So what will be the value for AF1 and AF2 individually? We can easily understand 2 and 2. Suppose that if AFT is equal to 5 given, so you can take under root 5 for first order high pass and first order low pass, no issue in that. But as far as this question is concerned, we can take AF1 equal to 2, AF2 equal to 2. Fine. Now again see, AF1 is equal to 2, one equation, two unknown. We can take this R1 less than 100 kilo ohm. Let's take this R1 is equal to 10 kilo ohm. So AF1 is 2, R1 is 10 kilo ohm. You can calculate the value of RF. So from here you can get the values of R1, RF, R and C for first order high pass filter. So you can see that this first order high pass filter, we know the value of R and C, R1 and RF. You can just mention the values of R1 and RF, R and C here in first order high pass filter. Similarly, you can go for design of first order low pass filter. So for first order low pass filter, the cutoff frequency in the question, it is given fh is equal to 1 kilohertz. fh is equal to 1 kilohertz. Now for first order low pass filter, fh is equal to 1 upon 2 pi RC. This is fh. Now again one equation, 2 unknown. You can take C. Let's say C is equal to 0.01 microfarad. Now you can calculate the value of R easily here. Now you know AF2, passband gain of first order low pass filter, that is 1 plus RF dash upon R1 dash. One correction is here, it is R dash C dash, because in first order low pass filter we have taken the notation R dash. For first order low pass filter we have taken the notation R dash, C dash, R1 dash and RF dash. Fine. Just refer this circuit again, R dash, C dash, R1 dash and RF dash. So again this AF2 is equal to 2. So let's take R1 dash is equal to 10K. So you can calculate the value of RF dash. So from here you can get all the numerical values for R dash, C dash, R1 dash and RF dash. It means that in this circuit we have got the values of R dash, C dash, R1 dash, RF dash. So from here we have got the component values, all the component values. Now you have to design this circuit, you have to draw this circuit, and you just mention all the component values in this circuit. This is the last step. And when you design this circuit on the breadboard in your lab, then after drawing the frequency response, you will get FL equal to 200 Hertz approximately. Obviously there will be some error, and FH is equal to 1 kilohertz. Fine. So here up to now I have discussed that how to find out the component values for a particular cutoff frequencies for wide band pass filter. So just firstly we have designed first order high pass, then first order low pass filter. Now coming to the next part of this question, that is draw the frequency response. So to draw the frequency response we need to draw this observation table. So in observation table the first column will be frequency F. Frequency F is the frequency of the input signal, right? And here in the question FL is given, that is 200 Hertz, FH is given 1 kilohertz. Now with the help of this frequency we can calculate mod V0 upon V easily, and further we can convert this ratio into dB, that is 20 log mod V0 upon V. Now we need to take some frequency values here, less than 200 Hertz, above 1 kilohertz and in between 200 Hertz and 1 kilohertz. Let's take one value 100 Hertz, then 500 Hertz, 700 Hertz, 2 kilohertz, 5 kilohertz, right? We need to take a few values by which we can draw the graph easily. Now we know the value of F, we know AFT, it is given in the question. We can calculate V0 upon mod V0 upon V. So the formula for V0 upon V is mod V0 upon V is, this is the voltage gain, this is the transfer function of the wide band pass filter, that will be the voltage gain of the first order high pass filter into voltage gain of the first order high pass filter into first order low pass filter. Fine. So V0 upon V for first order high pass filter, it is AF1 upon under root 1 plus FL by F square. This is the V0 upon V for, it is for first order high pass filter, where FL is the cutoff frequency for high pass filter, into AF2 upon under root 1 plus F by FH square, right? You can see that in the low pass filter the equation is F by FH square, but in the high pass filter the equation is FL by F, where FL is the cutoff frequency for high pass filter and FH is the cutoff frequency for low pass filter. So this is the equation of V naught upon V in for first order low pass filter. Now this is the equation for V naught upon V in. We know all the values. AF1 into AF2, AF1 into AF2, that is equal to 4. That is given in the question. It is very easy. FL is given in the question, that is 200 Hertz. FH is given in the question, that is 1 kilohertz. And what is F? F is the frequency of the input signal. Now you can just put the value of F and you can get the different values of V naught upon V in, and further with the help of calculator you can convert these values into dB. Fine. And after that, just plot the frequency response. It is the voltage gain in dB. Just mention all the points, right? And after mentioning all the points, you can get the response like this. Now here, if you do it practically, then this FL will be approximately 200 Hertz and FH will be approximately 1 kilohertz. Fine. So this is the procedure to draw the frequency response of band pass filter. Obviously in the pass band, this gain should be flat, that is called Butterworth response. Now coming to the next part of the question, that is the last part, that is the calculate the quality factor. So it's very easy. So if we know the formula of quality factor, we can calculate it. Quality factor Q is equal to center frequency FC upon bandwidth, where FC is equal to under root FH into FL, and as far as bandwidth is concerned, bandwidth is FH minus FL. So in the question, FH and FL are given. So just put FH and FL, you can calculate FC and bandwidth, and just FC upon bandwidth, it will be quality factor. So you can do it. Fine. So in this class, firstly I have discussed about active and passive filters. What are the advantages of active filter? Like it provides gain, there is no loading effect in active filter. And after that, types of active filters. Then I have discussed about wide band pass filter, how we can design the circuit of wide band pass filter. It's very easy, just cascade the first order high pass with first order low pass. And after that, I have discussed the design approach for wide band pass filter, and we have understood it with the help of this particular numerical. So from here, if we want to design a filter for a particular cutoff frequency, for that we need to calculate all the component values. Once we get all the component values, just draw the circuit and mention all the component values in the circuit. And after that, to draw the frequency response, so you need to draw this graph, and for that obviously you should know the equation for V naught upon V. Just use that equation and put all the values, and you can just get it filled with the help of a calculator. Fine.